Have you ever wondered how your computer's memory is organized and accessed? Let's dive into the world of memory models. At its core, a memory model is like the blueprint that dictates how a computer's memory is structured and how data is accessed within it. Different memory models define different addressing schemes, shaping how programs are written, compiled, and ultimately executed. Whether it's the flat memory model used frequently in modern operating systems, or the real-mode memory model, historically used in early IBM PCs, each model has its unique characteristics and uses. The choice of a memory model can significantly impact the efficiency and performance of a system. As we journey through our digital age, these models have evolved and adapted to meet the ever-growing demands of technology. Memory models have evolved over time, and we'll be taking a look at how this has happened. Back in the day, memory models were quite different from what we have now. Let's take a trip down memory lane and explore the early memory models that paved the way for the complex systems we encounter today. One of the earliest memory models was the real-mode memory model. This was a feature of x86 architecture and provided a 20-bit address space. What does this mean? Well, it could access up to a maximum of 1 megabyte of memory. Operating in real mode, however, did not come without its limitations. It lacked support for memory protection and multitasking, features that are integral to modern computing. Despite these drawbacks, the real-mode memory model was historically used in early IBM PCs and compatible systems. Now let's shift our focus to the segmented memory model. This model took a different approach by dividing memory into segments, with each segment having its own address space. This was a common feature in early x86 systems before the adoption of protected mode. This model was a significant step forward in memory management, as it allowed for a more organized way of accessing and storing data. However, the segmented memory model also had its challenges. The division of memory into segments meant that programmers had to deal with the complexity of managing separate address spaces. This often led to issues with memory fragmentation, where segments of memory went unused, leading to inefficient memory use. Despite these challenges, the segmented memory model was an important stepping stone towards the more advanced memory models we see in use today. So there we have it, a brief look into the past at the real mode and segmented memory models. These early models, despite their limitations, were instrumental in shaping the future of computer memory models. They laid the groundwork for the more complex memory models we see today, and their influence can still be seen in the memory management strategies of modern computing systems. These early models laid the groundwork for the more complex memory models we see today. As technology progressed, so did the need for more advanced memory models. Enter the protected mode memory model. This model, also used in x86 architecture, was a game changer. It provided a 32-bit address space, a significant leap from the 20-bit address space of the real-mode memory model. This meant that it could access a vastly greater amount of memory. But the improvements didn't stop there. The protected mode memory model brought with it features that revolutionized how we interact with memory. One such feature was memory protection, a mechanism that prevents a process from accessing memory that has not been allocated to it. This was a significant step towards ensuring the security and stability of systems. Another key feature was the support for virtual memory. This allowed systems to use disk space as a sort of faux memory when the actual memory was full. It was like having a backup plan when things got a little too crowded. This meant that programs could run even if they required more memory than was physically available, a crucial feature in today's world of multitasking and high-performance applications. The protected mode memory model also supported multitasking. This was essential as computers were increasingly used to perform multiple tasks at once. No longer were they single-purpose machines. They were evolving into the versatile devices we know today. In terms of organization, memory in this model was segmented. But unlike the segmented memory model, the use of a flat memory model was possible within each segment. This made it easier to manage and address memory. The protected mode memory model became common in modern operating systems, including Windows and Linux. Its features were instrumental in the shift towards larger address spaces and the support for multitasking in contemporary operating systems. The protected mode memory model was a significant step forward, but even more advancements were on the horizon. Most of the computers and devices we use today use modern memory models. One such model that has become a cornerstone of modern computing is the flat memory model. This model perceives the entire address space as a single, continuous block of memory. Imagine it as a vast playground where data can freely roam without any fences or partitions. There are no segments, no separate compartments, just a large flat address space. This model is the go-to choice for modern 32-bit and 64-bit operating systems that we use on our computers and smartphones. These systems require large address spaces to support the plethora of applications and processes they run. The flat memory model facilitates this by providing a broad, open playground for data to play around in. But the freedom of the flat memory model doesn't come without responsibility. With great power comes great need for management. That's where memory management units and operating systems step in. They ensure that each application gets its fair share of memory, keeping the playground fair and orderly. While the flat memory model is a crucial player in the realm of modern computing, it's not a one-size-fits-all solution. Different memory models cater to different needs and contexts. For example, in the world of embedded systems and microcontrollers, where addressability is limited, the banked memory model is often the model of choice. In this model, memory is divided into banks, and switching between these banks allows access to different portions of the address space. It's like having multiple playgrounds and being able to hop from one to another. Another example is the huge memory model, a variant of the flat memory model. It's commonly used in 16-bit programming environments and allows addressing more than 64 kilobytes of memory using a 32-bit address. The flat memory model is widely used, but there are other models that fit specific needs. Each memory model has its own strengths and is chosen based on the requirements of the system and the tasks it needs to perform. Sometimes a specific task requires a specialized memory model. Now let's delve into the intriguing world of specialized memory models, the banked, huge, and far memory models. To start with, we have the banked memory model. This model is a clever solution used in systems where the address space exceeds the size that can be addressed with the available number of bits. Memory, in this case, is divided into different banks, kind of like partitioning a hard drive. By switching between these banks, different portions of the address space can be accessed. This model is particularly useful in embedded systems and microcontrollers with limited addressability. Next up, we have the huge memory model. This model is a variation of the flat memory model, but with a twist. It allows addressing more than 64 kilobytes of memory using a 32-bit address. It is a common sight in 16-bit programming environments. You can think of it as a bridge between the limitations of 16-bit environments and the larger address spaces of 32-bit systems. It's particularly prevalent in some DOS-based programming environments. Last but certainly not least, we have the far memory model. This model is used in 16-bit environments and uses both a segment and an offset to address memory. It provides a compromise between the flat and segmented models, offering a unique blend of both worlds. It's like having the best of both, the flat and segmented models. This model is quite common in DOS programming. These specialized memory models are not as popular as their modern counterparts, but they hold their own in certain applications and environments. They are designed for specific tasks and can be incredibly effective when used correctly. These models remind us that there is no one-size-fits-all solution in the realm of memory models. These specialized models are crucial for certain applications and environments. So, we've taken a journey through the evolution of memory models. We've seen how these models have transformed from the simpler real mode and segmented memory models of the early computing era, which offered limited address spaces and lacked features like memory protection. We then delved into the transition to the more modern flat and protected memory models, which provide larger address spaces, memory protection, and support for multitasking, becoming ubiquitous in today's operating systems. We also explored some specialized models like the banked, huge, and far memory models, each designed to address specific needs in certain programming environments or hardware constraints. These memory models not only define how data is accessed and managed in a computer's memory, but they also influence how programs are written, compiled, and executed. Understanding how memory models work can give you a deeper appreciation for the complex world of computer architecture.